This is the first image released by the James Webb Telescope in 2022. If you take a small speck of sand and you hold it against the night sky and you look at it, you can just about understand about the size of the universe that we're looking at, a small speck of sand in the night sky. Yet, this image contains thousands of galaxies and billions of stars. And what's even more fascinating is that 95% of the things that should be here cannot be seen. And the reason is 95% of the universe consists of these things that we cannot see. It's called dark matter and dark energy. If we were to render a simulation, which is shown here, it's called the cosmic web simulation, we can start to understand how the universe would look like if we could see dark matter. The strands of purple here represent the dark matter, the mass that cannot be seen, and it holds up the structure of the universe itself in some ways. The galaxies are the bright little dots that I just shown. So how do we know that dark matter exists? Back in the 1970s, a famous astrophysicist, Vera Rubin, was trying to measure the effect of how galaxies are rotating around themselves. And her colleague noticed that the galaxies on the edge were rotating much faster than would be predicted by Newtonian physics. Over the next decade, they were able to measure this effect in 20 more galaxies, and they started thinking about what is it out there that we cannot see. These days, with much more advanced technology, we were able to actually try and measure what dark matter and where it is and what's the distribution. Here's an image from the Hubble telescope where the scientists used a tool called gravitational lensing, or technique. Gravitational lensing essentially looks at how light gets distorted by massive gravitational forces of the mass that cannot be seen to map out where this dark matter can be. So in this image, the bluer the area, the more dark matter there is. And of course, don't forget, dark matter is not seen. So this is just an overlay to make us understand of the scale of it. I think there's a very important lesson here to learn. If we want to understand and build a better model of the universe, we can't just look at things which are seen, but we have to think about things which are unseen, and we have to measure them. And by doing that and adjusting for the effects of the unseen, we're able to build better predictive models that can explain how the universe works. I want to take this metaphor and extend it to science as a whole. In my day-to-day life, I'm a researcher at Harvard Medical School. I train AI models on all sorts of medical imaging problems. Take it brain, kidneys, lungs, and then I use these models to help classify, segment all sorts of prediction models for disease in children at Boston Children's Hospital. Sometimes my experiments work, and I go and publish them in papers. But most of the times, those experiments don't really work out. So I initially stash them somewhere in my drawer, leave them somewhere in an unknown folder on my computer, and I let go. And I think we should think about science in the same paradigm of how we can think about the universe. Science can also be thought of consisting of two different things. There is the science that we see. Here are all the papers that were published, the 10 million papers in the open universe. Those are the things that we can talk about, things that we can contend about, things that we can discuss, criticize, try to reproduce. But science as a whole, just like the universe, has a lot of the dark stuff, dark matter that is not seen. The experiments that didn't quite make the cut. And those experiments are not just throwaway failures. It's just maybe you were looking at the data and the statistical significance didn't quite work out. Maybe you didn't set the parameters right. Maybe you couldn't reject the null hypothesis. Maybe you couldn't quite understand how to disentangle the signal from the noise in your model. But that information is very valuable. It's very valuable to us as scientists that we don't talk about, we don't really publish. And I think about it a lot. As I think about the next 5, 10 years of my life, I want to start a company that focuses on building the next generation of scientists. But the scientists that we're going to be building are going to be the AI scientists. So if we're going to be thinking about these kinds of problems, what are the necessary components of such systems? And one of these components, I think, is thinking about the unseen. If we want to build systems that become scientists or help our scientists, the human scientists, we need to think about how science is actually done. And it's through failures that we learn. There are many companies out there that are saying that we're going to build better logical systems, better LLMs, and we're going to set them off and train them on all of the world's published data. We're going to learn how to do really difficult problems in robotics, difficult problems in biotech, and we're going to reach AGI. I don't think this is quite there yet. I think if you want to become a scientist, yes, you should read the papers, but you should also go to the lab, do the experiments, fail, learn from your failures, and hopefully take it forward. So this is my message today. Thank you.